Hi everyone, I'm Hidehito Yabuuchi. Today I talk about our research, multi-resource low-latency cluster scheduling without execution time estimation. When using a computer cluster, users submit a job to the cluster. A job consists of several tasks, and each task demands various types and amounts of computing resources. Cluster schedulers are responsible for allocating the demanded resources to the tasks and manage their execution to minimize the latency of each job and achieve high job throughput. One of the characteristics of recent cluster workload is heterogeneity in both execution time and resource demand. First, most tasks have a short execution time, while a few tasks take a long time to complete. The figure on the left is a CDF, cumulative distribution function, of the execution time of the tasks on Google and Alibaba clusters. Although the length ranges are different, we can see that both clusters share the characteristic that most tasks have a short execution time. Short jobs generally have stringent latency requirements, so it is important to reduce the latency of short jobs. Second, tasks demand resources of multiple types, and their amounts are highly heterogeneous. The table on the right shows the statistic of resource demands of tasks executed on the Google and Alibaba clusters. In both clusters, each task demands two types of resources, CPU and memory. In the Google workload, the coefficient of variation of the CPU and memory demands reach up to 0.81 and 0.91, respectively. Moreover, the correlation coefficient between the CPU and memory demands are small in both traces. Cluster schedulers must consider this characteristic for efficient resource allocation. Existing cluster schedulers can be classified as shown in this table. In the first category, there are many cluster schedulers that require prior estimation of tasks execution time and perform scheduling based on the estimates. Prior estimation of execution time enables cluster schedulers to reduce the latency of short jobs by prioritizing jobs that are expected to be short. The accuracy of the estimation greatly affects the performance of this kind of schedulers. Unfortunately, existing estimation systems often fail to achieve sufficient accuracy, which leads to suboptimal scheduling performance. For example, short tasks will likely be blocked by long tasks at the front of a queue. To avoid performance degradation due to inaccurate estimates, several studies have proposed cluster schedulers that do not require prior estimation of execution time. They fall in this category. To reduce the latency of short jobs without degrading performance due to inaccurate estimates, these cluster schedulers first start running tasks, then observe their execution time, and prioritize tasks with short cumulative execution time. Existing schedulers of this kind, however, either do not explicitly handle resource allocation, or they assume that each task demands a single type and homogeneous amount of resources. Tasks in a real environment actually demand multi-type heterogeneous resources, and this characteristic should not be ignored for efficient resource allocation. So in this study, we propose a cluster scheduler that falls into the lower right category, that is, a cluster scheduler that does not require prior estimation of tasks execution time and can handle multi-type and heterogeneous resource demands. With this scheduler, we achieve the important goal of reducing the latency of short jobs. This is an architecture overview of our cluster scheduler. It has a two-level hierarchical architecture consisting of a central scheduler on a master node and a node scheduler on each worker node. Jobs submitted by users are first stored in a queue at the central scheduler in the order of their submission. The central scheduler distributes tasks in each job one by one to appropriate nodes. Then, the node schedulers locally manage the execution of the assigned task on each node. Upon a task assignment, a node scheduler starts the task if the node has sufficient resources available for the task's demand. Otherwise, the node scheduler tries to suspend one or more running tasks to make room for the new task. Waiting tasks are stored in a per node queue, and the node scheduler later tries to start or resume them. We divide the goal of reducing the latency of short jobs into two parts and address them in separate scheduler components. First, the central scheduler reduces the time from job submission to start by running as many tasks as possible simultaneously. Second, the node schedulers reduce the time from job start to complete. Let's move on to the details of each component. First, I explain how the central scheduler runs many tasks simultaneously. Running many tasks at the same time is, in other words, packing multi-tap and heterogeneous resource demands into node capacity. The central scheduler achieves this by defining similarity between a task's resource demand and its node's availability, and assigning the task to the node with the highest similarity. As an illustration, consider the situation shown in the right figure. The central scheduler is trying to assign a task to one of the two nodes. The right node has a higher similarity with the task because the task demands more CPUs than memory, and the right node has more available CPUs than memory, while the left one has lower available CPUs than memory. If the central scheduler assigns a task to the left node, which has lower similarity, then CPUs on the node are almost fully allocated to the tasks, while most memory is left unallocated. The central scheduler has to assign the next task to the right node in this case, and finally, the last task cannot be assigned to either of these nodes. On the other hand, if the central scheduler assigns the first task to the right node, which has higher similarity, then CPUs and memories on the node are allocated to tasks in good balance. In this case, all remaining tasks can be assigned to nodes. In this way, the central scheduler packs multi-tap and heterogeneous resource demand into node capacity. Specifically, given a task and a list of nodes, the central scheduler measures similarity scores between the task and its node according to this formula. The formula represents the dot product of the demanded and available resources. Then, the central scheduler assigns the task to the node with the highest similarity score. Next, let's look at the node schedulers. Node schedulers manage the execution of assigned tasks locally and reduce the latency of short jobs. To reduce the latency of short jobs without relying on the prior estimation of task execution time, we can use a scheduling policy called least assigned service, or LAS. LAS first starts running each task and at each point of time observe the task's cumulative execution time and prioritize tasks whose cumulative execution time is short. LAS approximates tasks' true execution time by their cumulative execution time. LAS prioritizes short tasks by utilizing preemption. When a node does not have enough available resources for a waiting task with a short cumulative execution time, LAS preempts one or more running tasks with a long cumulative execution time to make room for the waiting short task. LAS scheduling policy is useful but has a weak point. LAS can cause unnecessary preemptions when tasks demand heterogeneous resources, which is a situation we are tackling in this study. As an illustration, consider the situation shown in this figure. There are three running tasks R0, R1, and R2 in decreasing order of cumulative execution time. They demand different amounts of resources, which is depicted as the size of the rectangles. There is a stopped task, and because it has a shorter cumulative execution time than the running tasks, a node scheduler tries to preempt one or more running tasks and resume the stopped one instead. The naive employment of last policy will greedily preempt all running tasks before it obtains sufficient resources for the waiting task. However, R1 does not need to be preempted. Preempting only R0 and R2 offers sufficient resources to meet the waiting task demand. To address this issue, we make a modification to last scheduling policy. The modified last efficiently reduces the number of preemptions by finding a set of running tasks to be preempted, just enough for resuming a waiting task. Specifically, the modified last scans the running task in a certain order to find the minimum set of preemption targets to resume the waiting task. First, it checks whether R0, the running task with the longest cumulative execution time, will offer enough resources to resume the waiting task. If not, it next checks the next longest running task, R1, will offer enough resources. Then it combines R1 with other running tasks whose cumulative execution time is longer than R1. In this figure, R0 has a longer cumulative execution time than R1, so the node scheduler checks whether the combination of R1 and R0 will offer enough resources. The node scheduler continues this process until it finally finds that the combination of R2 and R0 will be enough. Before we move on to evaluation, let's summarize the design of our cluster scheduler. It has a two-level hierarchical architecture consisting of a central scheduler on a master node and a node scheduler on each worker node. The central scheduler distributes tasks to nodes so that it will reduce the time from job submission to start. This is done by packing tasks, multi-type, and heterogeneous resources demands into node. The node schedulers manage the assigned task on each worker node so that they will reduce the time from job start to completion. The node schedulers search for the minimum set of tasks to be preempted to reduce unnecessary preemptions. We experimentally evaluated our cluster scheduler to measure its performance. We implemented our scheduler by extending Yarn, the resource manager for Hadoop. The evaluation setting was as shown here. We used a computer cluster consisted of 32 bare metal nodes, each having 32 threads and 64 GB memory. We generated a realistic workload based on the Google cluster trace. We compared our scheduler against Capacity Scheduler, which is a Yarn's default scheduler, and Kairos. Kairos is a preemptive cluster scheduler that does not rely on the prior estimation of task execution time. We modified Kairos naively so that we could input tasks with multi-type and heterogeneous resource demands. First, as an end-to-end performance criterion, we evaluated the cluster scheduler based on the distribution of slowdown rates. The slowdown rate of a job is defined as the actual job latency divided by the hypothetical execution time if the job was executed alone on the cluster. So the distribution of slowdown rate is an index for measuring latency with emphasis on short jobs. This figure plots the CTF of slowdown rate for the workload. The more to the left a line is, the more the scheduler reduces the latency of jobs. Our scheduler significantly reduced the slowdown rate compared to Yarn. Compared to Kairos, our scheduler reduced the 19th percentile of slowdown rate by 6.4% and the 19th 9th percentile by 29%. Our scheduler was more effective in reducing tail latency. the maximal slowdown rate was 47% lower than that of Kairos. One reason for the improvement is that the central scheduler distributes tasks to nodes so that as many tasks as possible will run simultaneously. This figure shows the numbers of running tasks on the cluster with Kairos and our scheduler during the experiment. The line shows the average of all nodes, and the field ranges show the intervals of two standard deviations from the average. Our scheduler executed more tasks than that of Kairos with less deviation. This result implies that our scheduler successfully reduced the time from job submission to start by distributing tasks based on the similarity between resource demand and availability. Another reason for the high performance of our cluster scheduler is that the node schedulers reduce the number of preemptions, which allows more tasks to continue running without interference. This figure shows the distribution of the numbers of running tasks preempted together in a preemption process to make room for a waiting task. With our scheduler, 95% of preemption processes preempted only a single running task, while with Kairos, the percentage was 79%. The total number of preemptions was reduced by 38.3% by our scheduler. We can say that our scheduler successfully minimized the number of tasks preempted by examining the heterogeneous resource demand of waiting and running tasks. Finally, we measure the effectiveness of our cluster scheduler when workloads have higher heterogeneity in tasks' resource demands. To do so, we modify the standard deviations of the CPU and memory demands of the generated workloads by various scaling factors. This figure shows the distribution of slowdown rate while varying the scaling factor. A larger scaling factor indicates that workload had a higher degree of heterogeneity. With Kairos, the slowdown rate increased and the degree of heterogeneity increased. In contrast, our scheduler maintained low slowdown rates almost regardless of the degree of heterogeneity. This result suggests that our scheduler minimizes the impact of high heterogeneity in resource demand. Let me conclude. We propose a cluster scheduler that does not require the prior estimation of tasks execution time and can handle multi-type and heterogeneous resource demands. Our scheduler consists of a central scheduler and node schedulers on each worker node. The central scheduler reduced the time from job submission to start by packing tasks into nodes. The node schedulers reduce the time from job start to complete by minimizing the number of preemptions. Experimental evaluation shows that our scheduler was able to reduce the latency of jobs, especially for short jobs. The 19th percentile of slowdown rate was reduced by 6.4%, and the 99th percentile by 29%. That's all for my presentation this time. Thank you for listening.